degrees of freedom, we will find that the space-time is discrete and it has microscopic degrees of freedom. We will also find, and I will give you indications of that in the talk, that the universe has its own dynamic, and you shouldn't be studying universe at very large scale, very large scales, as a special solution to Einstein's gravity, which is what we are doing currently, but it should be done by an intrinsic description. The cosmos has a life of its own. So both these results essentially come from the fact that in the next 100 years, already there are signs that GR requires another paradigm shift. This arises from the fact that there is enough internal evidence in the structure of classical GR itself to suggest that classical gravity, the field equations of classical gravity, has the same conceptual status as the equation describing hydrodynamics or fluid dynamics. An immediate consequence of this is that if you go about quantizing gravity by treating the metric as a degree of freedom and trying to sort of quantize it the way we have done it in many other gauge fields, for example, you will fail. Because this is like quantizing the equations of elasticity. You will discover phonons. You will find very interesting quantum phenomena involving phonon-phonon scattering, phonon creation, etc., etc. Very exciting, but that is not the physics of atoms. So in the same way, if you quantize gravity, you are quantizing elasticity of space-time. You will get gravitons and graviton physics, but that is not the space-time, the physics of the atoms of the space-time. The approach that there are these microscopic degrees of freedom and they come about in a particular way has actually become quite fashionable in the last 10 years or so, and almost everybody agree that we need some kind of paradigm shift in gravity. What I am going to talk about today is the program which some of us have been involved in, the work by me and my collaborators. And this distinguishes itself from many other approaches by many other people by 3 key ingredients. So I am going to first run over the 3 key ingredients for the sake of non-experts who may miss the details between different approaches. The first key ingredient is that suppose you obtain some kind of thermodynamic derivation of Einstein's field equations. You have completely lost the battle. Einstein's field equations equates a geometric quantity to the energy momentum tensor. Its interpretation is geometrical. It is not thermodynamical. The first and foremost is that space-time dynamics itself should be described in thermodynamic language, not in geometric language. Idea is not to derive Einstein's equation as GAB equals some TAB from some thermodynamic argument, but to reinterpret this equation in entirely thermodynamic language. That is what we have been doing. Second is that the connection between gravity and thermodynamics transcends general relativity. In particular, in general relativity, there is a result that the entropy of horizons, in particular, for example, black hole horizon, is proportional to area. This is a result in Einstein's gravity. There is a whole class of theories called, for example, Lovelock models, in which the entropy is given by an expression like this. The entropy density is proportional to some area element, but involves a very complicated tensor which occurs in that theory. So the idea is that this connection between gravity and thermodynamics is applicable to a much wider class of theories, because area is such a nice object that once entropy is proportional to area, there are hundreds of ways in which you can derive various things. But your idea should work even in a context where the entropy is not proportional to area, and that is another key ingredient in the approach which we have been taking. And the last one is that physics is about getting numbers and making predictions which are possibly falsifiable. So it is not philosophy, it is physics. So you have to finally get something more than what you put in. For example, I can write Einstein's equation very elegantly like a thermodynamic language, but that is like taking Maxwell's equations in component form and writing it in vector notation. The physics hasn't changed. So you really have to get something more out of what you have put, and this approach does that. Firstly, it gives you insights about the classical gravity itself, which you couldn't have guessed before. It tells you something about the microscopic structure of space-time coming from up downwards, and it also tells you something very interesting about the cosmological constant and the information content of the universe, which I will come to in the end of it. Okay, so now let us get on with it. The key idea of thermodynamics, which distinguishes it from standard mechanics, is that more is different. When there are large number of degrees of freedom, a new player enters the scene, what I will call the heat density. The heat density is essentially Ts per unit volume, and for most of the ideal fluid kind of matter, it is energy momentum tensor dotted with a null vector, and it is given by P plus rho. This particular object is the difference between energy and the free energy, and the concept of energy being distinct from free energy is a thermodynamic phenomenon. And normal matter, a glass of water, has heat density. This heat density is related to entropy density, which is related to information density, and it is related to the microscopic density of states. So I will use these expressions in some sense of conceptual equivalent. Mathematics will take care of itself. Conceptually, they are all talking about the same thing. What is interesting is that this fluid called space-time also has a heat density. So you need entropy and you need information connected with this fluid, and the question is, where does it come from? So the fact that there is entropy and temperature, most people who are not experts in this field will know that it is associated with black hole physics, but it is certainly possible to associate it with every event in space-time for a particular class of observers. So I want to run you through that argument first. When you do that, you will find that the description is very similar to what you do in condensed matter physics. The temperature is completely independent of theory of gravity. All the information about the theory of gravity is encoded in the form of the entropy functional. I can have this plastic material and a glass of water and a metal rod kept at the same temperature. So the temperature doesn't tell me anything about whether it's plastic or metal or a glass of water. But if I give you the entropy functional of that system, then I know what is what. So exactly the same thing happens when you are describing the space-time. The entropy comes in into this game because there are regions of space-time which can be inaccessible to certain class of observers in any space-time. This inaccessibility translates into entropy. So obviously the information content of space-time plays a central role, and one message we get out of this is that one should no longer think of non-inertial frames and different class of observers as just coordinate relabeling, which we general relativists tend to do, and that is not the case. It acquires a more fundamental significance. As we go along, we will see that. But where does temperature comes from? The temperature comes from what I personally consider to be the most beautiful result which we have when we put quantum and general relativistic principle together. If you have an observer who has an acceleration of some kind, it appears in different contexts in different ways, in cosmological horizons, in black hole horizons, when somebody is accelerating in flat space-time, etc. In this context, it goes under the name Andrew-Davis effect, after these two gentlemen who discovered it. It tells you that this acceleration g is related to a temperature like this. So if you take a glass of water and you run with it, its temperature will be different from if you are not running with it. And that temperature equivalence is going to play a very key role. So we have information which translates into entropy, and we have the temperature, so you have a heat density which you can associate with every event in space-time. So let me try to explain to you where this comes from for those of you who don't work in this area. So this is a space-time diagram, and this is an event, and these are the null rays going through the event in some crazy form. You go to a locally inertial frame, that is the frame of the freely falling observer out here, and once you go to the freely falling frame, which is valid in this region, the light rays become 45 degrees. Now at any given point in that freely falling frame, you can also have an observer who is just sitting quietly compared to the freely falling observer. This guy is accelerated with respect to the freely falling observers. What you will find is that the vacuum fluctuations of this observer measured in this region will appear to be thermal fluctuations for this observer. This is an extremely non-trivial equivalence, and this is what gives you the relationship between this temperature and the acceleration. So this also introduces the quantum field theory in freely falling frame, introduces H cross into the system, and you have a H cross by C coming in. Let us watch out for these constants as they appear. Now this introduces the concept of what I would call the local Rindler observers. This is a major contribution to this field from Ted Jacobson. He pointed out that if you have a horizon or a null surface and matter is crossing that, then you can associate a heat density with that matter vis-a-vis the observer who is seeing this null surface as a horizon. This also translates in a very remarkable way when you Euclidenize the space-time. So I won't have too much time to discuss it, but let me just mention that a null horizon is a solution to x square minus t square equal to 0 in Minkowski space. When you go to the Euclidean space, you change this sign of this to plus t square, that just maps to the origin. So a hyperboloid out here with a normal to it will map to the origin, and the normal wouldn't know which way to look. This will play an important role when we go along further. So now that we have temperature and entropy and this concept brought into the space-time, let us ask, why is it important to be hot? This has to do with the fact that if I give you a glass of water, you could have figured out that the water is discrete degrees of freedom exist in this glass of water, and there are molecules in this glass of water without doing experiments at angstrom scale, where you actually see the molecules. And this is precisely what Boltzmann did. If you read the history at that period, he cut the Gordian knot and stopped all the confusion about the nature of heat by just saying that heat is the energy of the microscopic degrees of freedom due to their motion or whatever. So there are if you can heat anything, it must have microstructure, and in microstructure we store it. What is more, he also gave a formula which is delta E divided by half kT is delta N. This is the number of degrees of freedom you need to store this much of energy at this temperature. We usually write it as delta E equals N kT. That is a wrong way to think about this. In this way, the right hand side is purely thermodynamic. They are defined in the thermodynamic limit. Left hand side has absolutely no meaning in thermodynamic limit. This is statistical mechanics. It is actually telling you the number of degrees of freedom. So this is the connection between the thermodynamics on one side and statistical mechanics on the other side. But now we just saw that you can also heat up the space-time. So do we have a similar result for that? Can I count the number of degrees of freedom in the space-time? Yes, you can. It turns out that when you do, you get a result. In the normal case of a fluid, the degrees of freedom scale as the volume. Here you will find that the degrees of freedom scale as the area. The energy in the bulb is related to the temperature as measured by its boundary surface divided by the number of degrees of freedom, which is area divided by LP square. That is, an area dA is endowed with the degrees of freedom, which is dA by LP square, and you get this result. I will in a minute present it in a nicer way. But let me tell you, I'm not going to repeat this all throughout. Virtually everything which I am saying can be extended to a much wider class of theories called Lovelock models. Here the number of degrees of freedom per unit area will have a more complicated expression. So I told you right at the beginning that the thermodynamic ideas transcend general relativity, and this is one of the indications of that. Let me get it back to the space-time diagram and present this in a different way. So here is the normal space, 3 spatial axes, and this is the equipotential surface, 2-dimensional surface in this space. And at every point in the area, I am associating with this area a number of degrees of freedom, which is A divided by LP square. At every point there is an acceleration due to gravity, due to matter inside, and these are the guys who are sitting there who are feeling that acceleration. There are also freely falling observers at every location. So if you compare these two, there is a local Andrew Davis temperature, which is G local divided by 2 pi, and you can also define an average temperature on this surface. So this equipotential surface is endowed with an average temperature. Think of that as a microwave oven kept at this temperature. Now if there is matter inside which is in equipartition with it, the number of degrees of freedom in the bulk will be this E divided by this average temperature. What is remarkable is that in any static geometry, the number of degrees of freedom in the surface and the number of degrees of freedom in the bulk measured by, defined by these two relations are equal. Einstein's equations implies this result, and if this result holds for every equipotential surface in a static geometry, that in turn implies the Einstein's equation. So what we have got now is a completely thermodynamic way of thinking about Einstein's equation. All static geometries has an equivalence between the number of degrees of freedom in the surface and the bulk, and the evolution arises when these two are not equal. The difference between them involves some kind of a time evolution, which in turn involves heating and cooling of the space-time. In fact, that also you can figure out, and every geometrical variable which we are familiar with can be given a thermodynamic interpretation. You will find that in this was worked out, for example, in this paper. Take the metric and convert this into this variable, which turns out to be more convenient, and instead of the standard Christoffel symbols, use this linear combination. It turns out that these variables, this Q and P, Q delta P and P delta Q with indices contracted suitably, corresponds to S delta T and T delta S of the thermodynamics of the null horizon. So this is a very generic result. So this particular quantity you have here, Q delta P, is like S delta T. This change in the temperature. This is number of degrees of freedom. You have certain number of degrees of freedom and you are heating it up, so its temperature is changing. What you can show is that the entire content of Einstein's theory, the dynamics, we are no longer talking about static situations. Dynamics can be converted into the heating or cooling of the space-time, where this essentially corresponds to S delta T of a boundary, where it is driven by the difference between the number of degrees of freedom in the surface and number of degrees of freedom in the bulk. So this deviation between this equality is what is driving the dynamics of the space-time. This is the content of Einstein's equation, and again it is implies and implied by Einstein's equation. So this is described completely in thermodynamic language and not in geometric language, and this is what I said is the first key ingredient in this entire approach. You need that. You don't want to tinker with geometry after saying that space-time is thermodynamical. Okay, let us go a bit further. I said it also gives you insights into the nature of the general relativity itself. One of the things, I'll just briefly go over it. It tells you that there is a natural definition of the momentum associated with a space-time by a given observer. So if you take normal matter, it has an energy momentum tensor which satisfies this equation. The momentum associated with this energy momentum tensor requires an observer to be introduced. The observer with a velocity v will associate this much of momentum density with it, and that will not be conserved. That is not conserved because you have not taken into account the momentum of gravity. Einstein's equation can be recast as a pure conservation law for this momentum. This is the normal momentum of the matter as measured by an observer. This is the momentum for the geometry which an observer with a velocity v will attribute to, and it is given by this expression. You notice exactly the same structure here. If I multiply by root minus g, this is some kind of a thermodynamic momentum, and this is the geometric momentum. And this particular combination, the conservation of this, validity of this for all observers is equivalent to Einstein's equation. What is more, the equation I told you in terms of n surface and n bulk can be recast in the following way. When the field equations hold, the heat content of the boundary is equal to the energy content in the bulk. Remember this, because when we do cosmology, this is going to play a crucial role. Okay, now let me go further. One more side comment. The Newton's law of gravity comes about in a completely different way here. The constants we have introduced are h cross c and Lp square. This comes from entropy, the other two come from temperature. And Newton's law of motion is m1 m2 upon r square with this combination. It does not have a h cross going to zero limit. Don't rewrite this in terms of capital G. That is what Mr. Newton did. But the right way of thinking about space-time is like this. It has no h cross limiter. Space-time and gravity is intrinsically quantum, just like matter is intrinsically quantum. If you take h cross going to zero with a solid piece correctly, all the atoms will collapse because the h cross inside the atoms are also going to vanish, and that is exactly what happened. Matter and geometry has to come together. This is again something which we will see later on when we look at cosmology. Okay, so this is again a side comment that once you have got this thermodynamic language and you have the Einstein's equation interpreted in thermodynamic language, you can also write a variational principle entirely in thermodynamic language in terms of the dissipative heat on every null surface, and the extremizing that will give you the field equation. Once again, it works for a wide class of gravitational theories, and the entropy density of the theory defines what theory it is. Now, when you do it this way with this heat density, a completely new feature emerges. We always thought that gravity is generated by energy momentum tensor and gravity responds to energy density. No. Gravity responds to heat density because gravity is thermodynamical. Gravity responds to this quantity in this approach. So this is the only difference from Einstein's theory. Cosmological constant has this side strictly zero. It has zero entropy. So the cosmological constant does not come into the field equations, but when you integrate the field equations, it arises as an integration constant, which means the same approach should provide you a way for evaluating its value. You need a new physical principle to determine the cosmological constant, and I will tell you as we go along how that comes about. So the next question is, can we probe these ideas a bit further? So I have said that there are atoms of space-time and gravity is completely thermodynamic. So can I have an insight into the statistical mechanics of these microscopic degrees of freedom? Can I, for example, write down a density of states for space-time plus matter and extremize it to get this dynamics? Indeed, you can, but what you need now is that you need to be able to count the microscopic degrees of freedom without actually knowing the quantum theory of gravity. This is exactly what Avogadro's and Boltzmann's did. They counted the number of internal degrees of freedom even before they knew what atoms and molecules are. If we can do that, if we can get this number of degrees of freedom of space-time and then multiply it by matter, this part is known, and then maximizing this should give you the field equation. So can you do that? In fact, you can, and we have been doing it all along even in our undergraduate physics, but people probably haven't learned it like that. Suppose you have a fluid which is flowing. There is normal fluid, water flowing. At the most coarse-grained long wavelength limit, you will describe it by continuum field equations like Euler equation and continuity equation, where there is a single velocity vector at any given point. This is the flow velocity of the fluid, there is density, etc. There is no velocity dispersion. So if you want to write down the fluid equation, things like temperature, which comes from velocity dispersion, has to be added in by hand. All the constitutive relations has to be added in by hand, and you do this. But there is a slightly deeper level of description still possible, where you use a distribution function. The distribution function is a remarkable object. It counts what you cannot count. It tells you number of degrees of freedom or the number of molecules at a point x with a momentum p in d3x, d3p. This d3x, d3p is not a mathematical infinitesimal. It has to be a physical infinitesimal so that it can contain sufficiently large number of molecules. Now at any given point there is an extra degree of freedom, a vectorial degree of freedom, which is this momentum p. These are the momentum vectors associated with the molecules at this point. Atoms with different pi can exist at the same xi. So we need to search for such a degree of freedom or have to obtain such a degree of freedom in the case of gravity to count these degrees of freedom. How can you do that? How will you do it in fluid? You take surfaces and then you keep counting the total number of degrees of freedom inside and you collapse the surface to this point. This is exactly what we want to do in the case of gravity to get the atoms of space-time. So you want to find this particular concept as to how to count these microscopic degrees of freedom. But here I need to introduce one extra description. Unless there is some way of discretizing the space-time, unless the space-time knows it is discrete, you are not going to get this thing. You will just get 0 degrees of freedom. So for that I have to introduce a 0-point length, and let me briefly describe what this is. It might even feature in Dawood's talk later on today. We are normally accustomed to learning general relativity in terms of a metric tensor, but there is a completely equivalent description in terms of what is known as the Singer's world function. This is the geodesic distance between any 2 points. Given the metric, this formula tells you how to compute it. And given this sigma square, you can compute GAB. So the description in terms of this quantity is completely identical mathematically to the description in terms of the metric tensor. Except that there is very strong evidence from different approaches to quantum gravity that the discreteness modifies this sigma square to some other function of sigma square, such that when sigma goes to 0 classically in the space-time, there is some 0-point length which survives. I will not go into describing this in great detail. You can find it in various papers here. This sigma square was associated with a metric here, and this modified S of sigma square will be associated with another metric which we call the Q metric. So there is an L0 which is essentially related to the Planck length with some numerical factors. Using this idea, you can replay exactly the same game, and when you do that, you can try to associate an area or a volume with a point, and you get a remarkable result that points have still 0 volume even after this discreteness is thrown in. Because I have a modified metric, I can do all my geometry with that. But it does have a finite area which is given by this, and the density of states of quantum geometry, logarithm of that, log of omega, this is Boltzmann again, is essentially the area associated with this event, and you can work through the mathematics and you will find that the log of this omega is given by this expression. And a new degree of freedom emerges by the calculation, which is a fluctuating null vector field, which is just like the fluctuating momentum vector field at every point for the molecules in a fluid. And its state depends on the state of the quantum geometry, and you can work with this object. So now when you do this, you also find that the Euclidean origin maps to the Rindler horizon, and this sigma square actually picks up the null vectors. That is, this vector, I showed you this picture before, goes into the null vectors of this geometry. And you can, if you vary these total degrees of freedom, you essentially get back the Einstein's equation in thermodynamic language with an undetermined cosmological constant, which I have written here in the geometrical language just for your convenience. But as I said, it should be interpreted in thermodynamic language. There is also 2 more pieces of extra bonus which comes out of this approach. First is that you find that close to Planck scale, the description of geometry, which no longer exists because we are almost entering a pre-geometric phase, is 2-dimensional. There were evidence for this from work by a very large group of people, and we also obtain it in this. Second, a fundamental constant, which is just 4 pi, appears as the basic quantum of information in this approach. So if you take a sphere of radius LP square and you divide its surface area into units of LP square, you get this number. So this arises naturally in this approach as a unit of information. Now in the last part of my talk, I will describe to you what is the new thing which comes out of it. I told you that you should be able to make falsifiable prediction and you should get more than what you put in. This happens in cosmology. The conventional universe in the conventional way of description has three phases. First, there is a quantum gravitational phase. We really don't know where it kicks in, but probably below something like 10 to the 19 GeV. Second, there is so this is the first constant about the universe. The universe is described by three signatures. This is the first one. The second, there is a conserved number in the universe, which is the matter density to the power 4 upon radiation density to the power 3. This is independent of the epoch. Astronomers who were living in a galaxy at a redshift of 8 would have attributed to the universe different omega baryon, different omega dm, different omega, various omegas and h naughts and all these constants. But they will all get the same number for this because this number doesn't change with time. And this number are unique to our universe. And we now know that there is also one more number. If the dark energy is cosmological constant, which I believe it is, there is yet another number. These are the three numbers which essentially tells us what our universe is. So we need to explain this. And one density you can take as the scaling density, rho qg. Then you need two densities to be described. This, in the conventional approach, is related to the baryonic and dark matter particles, and there is a hope that high energy physics will eventually fix this value. I will not say anything more about that. But we have absolutely no clue as to even how to go about it, about the cosmological constant. Where does this number come from? So let us see whether we can get something out of it. This is what is considered to be the cosmological constant problem, but I believe we have sort of misunderstood the problem itself. This is because we should not be describing cosmos as a special solution to gravitational field equation. If you take the thermodynamic approach, incidentally, I couldn't resist showing this equation. The entire thermodynamic approach becomes extraordinarily simple in the cosmos, and it is the Einstein's equation reduces to these two equations. This is the volume of the Hubble sphere. The rate of change of the Hubble spheres is given by n surface minus n bulk, as I defined before. When n surface becomes equal to n bulk in the asymptotic future, it will be a de Sitter universe, and it is tending towards it. It is driven by this difference. Second, the total energy inside the Hubble sphere is just equal to the heat density on its surface. These are the two results which I gave you in a very general context, but in this particular case of the universe, this is what it comes from. So this is just a geometrical way of doing this. What we expect to see is that there will be corrections to this, and this is important. In our entire approach, the Einstein's field equation, to which these equations are equivalent to without the dot dot dot, arises out of the thermodynamic equilibrium result. Thermodynamic equilibrium, we know, breaks down even in the case of, let us say, normal fluid systems. Astrophysicists are very familiar with it in two cases, not one. First, something which everybody knows: if you go to smaller and smaller scales and if you hit mean free path, you don't have thermodynamics. This is like probing deeper and deeper and going into Planck scales, and then you cannot use Einstein's field equation. But there is another thing: if something local, something happens here, then it takes some kind of an equilibration time scale, and only up to some region the fluid could have come into equilibrium. This is what happens in the case of the universe. Very large scales of the universe are out of equilibrium, and it has to be described differently, and that is what these dots denote for you. Figuratively, think of the universe here. This is the surface, and you are here. If you go out and see, at a redshift of 1000, you will see the cosmic microwave background radiation. Assume for a minute you have some way of probing even further, non-electromagnetically, for example, and you will see the electroweak transition taking place in the sky. You just have to go up to this. Go still further, you will see grand unified scale written down there, and let us assume no such thing like inflation took place. Then, at the boundary where the Big Bang should be, you will see the quantum gravitational effect. So quantum gravity is encrypted right on the surface of the sky. You just have to go further and further and deeper and deeper. Beyond that, X is a pre-geometric phase, which roughly speaking I call ice, and there is an emergent phase which I call water. Here the equilibrium Einstein's equation hold. Here we do not have a geometric description, and all indications are that the effective geometric description will be two-dimensional, and it will probably be even compact. So if you have that kind of a picture, then what connects this pre-geometric phase with the emergent phase is two numbers. One number is the value of the cosmological constant. Another number is that the quantum fluctuations on this phase is going to give you a fluctuations which we know how to measure, and it is about 10 to the minus 5. So we want to know these are the two numbers which comes from the quantum phase, and we should be able to relate these two. This is a completely new idea. So let me try to tell you how this comes about. This has to do with the accessibility of information to an observer. So if you take an observer and you look at the co-moving distance light would travel between T1 and T2, you have an expression like this. And you think of an observer who is waiting for a very long time, some kind of an eternal observer to whom I am taking T2 to infinity. And you ask what is the maximum co-moving distance signal would travel if it was emitted at a point at an epoch A. This is the expression for this. This expression is infinite if the universe was, let us say, radiation or matter dominated, and if there is no lambda. And it turns out to be finite if lambda is not equal to 0. This is essentially that de Sitter universe as a horizon, and it has its own thermodynamics, and it is just another way of saying that equivalently. So pictorially what happens is that if I take log A on this side and co-moving scales in this side, there is a pre-geometric phase which is purely quantum gravitational, and there is a quantum classical phase which kicks in at some A, let us say. Then there is a radiation dominated phase, matter dominated phase, and lambda dominated phase. And the co-moving Hubble radius sort of turns around like this. Co-moving length scales of course stay put, and the edge of the visible universe follows a curve like this. Now if you look at different degrees of freedom which are encoded in the fluctuations of matter fields which came into being along with geometry at this time, these things will enter the Hubble radius at these points. These are just co-moving scales staying put. They will enter the Hubble radius. All the degrees of freedom in this region will enter, this will not. So I can count how many degrees of freedom are entering the Hubble radius, and I can use that to define an information content. So the information content accessible to an eternal observer is given by the number of modes which enter the Hubble radius. And if you work it out, it turns out to have this expression where these are co-moving Hubble values at this point h lambda, at this point h lambda, and h qg. Now that can be translated into standard expressions which I have given. It will involve rho lambda, rho eq, and the energy scale at which this phase transition from pre-geometric to normal phase took place. But we don't know what this energy scale is, but you can relate that energy scale to the amplitude of fluctuations. Then you get a remarkable result. This is the amplitude of that fluctuation. This is rho eq, which is a known quantity. This is Planck length. Rho lambda to Lp to the power 4 is given by this times the information content, this IC defined here. It's just this equation written differently coming up here. So if IC is infinity, if an eternal observer has access to infinite amount of information, all the modes are entering the Hubble radius, then the cosmological constant will be 0. This is infinity, gives you this is 0. If the cosmological constant is finite, then this has a particular value. Given the value of IC, I can calculate the value of rho lambda because other things are known, or in terms of A and rho eq, or at least I can relate the amplitude of fluctuation, rho eq, and rho lambda together if I know the value of IC. At this stage, of course, since I know all these quantities and this from cosmological observations, I can go and compute IC. But that is a bit of a wimpy way of doing things. What we want to do is to make a prediction. We know that there is a quantum of information which is IQ is 4 pi, plug it in, then you get a formula here. You can go and check whether this is correct. This is measured, this is measured, this is measured. Therefore, you can ask whether this equality holds or it doesn't hold. it turns out that it holds to remarkable accuracy. So let me show it to you in graphical form. This is the measured value of rho bar EQ is the measured value of rho EQ, and this is what our universe has. This is what our universe has, and I can plot in this contours of constant A, which is just some particular combination of this being plotted, and it goes plumb through this for the observed value of the amplitude. Now, of course, cosmology is very precise, but still we have errors. So the band in which we are living today is here with lavish accounting for the errors. This is the error bar on rho lambda, this is the error bar on rho EQ, we are in this red box, and the error bars on these amplitudes gives you these lines. So we have to be inside this. In principle, you can have a universe when the observations are very precise, which puts it here. That throws out this model. The model says that only this is allowed, and there are other regions which are currently available, because in the current conventional cosmological model there is absolutely no relation between A, rho lambda and rho EQ. A is something completely different which comes from inflation, etc., etc. So as a result of which you can't draw a box like this, and this is what we can do here. There is another way of doing the same thing. You write down this IC in terms of these quantities, and I told you that these quantities are all measurable. So this completely weird combination, 2 over 3 pi times logarithm of some object with a constant here which has this kind of a value, we predict should have a value equal to 4 pi. So you can go and observe these things, plug it in and ask whether it is 4 pi. You find that it is 4 pi to 1 part in 1000. This is either an extraordinarily cruel trick nature is playing on us and it is a complete coincidence, or it is telling us something very deep. And I certainly believe it is trying to tell us something very, very deep. Okay? So this is essentially the information content of the universe which is coming from a pre-geometric phase to this phase through this. Okay, let me now summarize what I have been saying. The gravitational dynamics arises from a thermodynamic variational principle, and it can be related to the kinetic theory of atoms of space-time. So it would be lovely if I have a quantum theory of gravity and I can do everything from bottom upwards. I don't have that, but in top down from classical gravity, which is thermodynamic limit, I'm just going to the next level, which is sort of kinetic theory, and this kinetic theory limit, and from that I have a complete description of the equilibrium statistical mechanics as well as the thermodynamics. Now, we all know that equilibrium statistical mechanics is very powerful in the sense that it also encodes fluctuations around equilibrium, which means that in principle my formalism will also tell you corrections from the fluctuations around equilibrium. It turns out to be mathematically extremely complicated to do that, but that is a hope for the future. Second, the evolution of geometry should be taught and thought of in a completely thermodynamic language, and it is related to the information content of the space-time. So there is a surface degrees of freedom and a bulk degrees of freedom, and their difference is what is driving the evolution of the space-time. And this particular principle becomes enormously simple when you do it in the context of cosmology. The only difference, I said that we are reinterpreting Einstein's equations in thermodynamic language, but when you do that, Einstein's equations do not couple, or rather the geometry does not couple in the Einstein's language to energy density, but it couples to the heat density. And the heat density is rho plus P, and that is strictly 0 for a cosmological constant. So the cosmology constant is sort of, the theory is immune at the tree level to this cosmological constant. And what happens is that it reappears as an integration constant. This is what happens in a class of theories called unimodular theories of gravity, except that here it happens in a much nicer way. And what is more, you cannot just leave it like that and say, oh, somebody has to tell me cosmological constant and I will plug it into my paper. You need a principle which will fix this, and it is related to the information which is accessible to an eternal observer. You can do that, and we do get an idea for that, and it gives you the correct value of the cosmological constant. So if anything else, this is the formula which you should take home with, especially the cosmologists in the audience. This is known, amplitude of fluctuations is known, you know how to take logarithms and multiply by 2 over 3 pi. You do it at your leisure, you will find it is 4 pi. Then you put the uncertainties in cosmic measurements and you will find that it is 4 pi to 1 part in 1000. Finally, at Planck scales, it gives a completely different picture of the universe. The Big Bang gets replaced by a pre-geometric phase, and the pre-geometric phase cannot be translated by definition into geometric language. But if you want to give an effective geometric description, it is two-dimensional. And we know that two-dimensional Einstein's equation should have 0 on the right-hand side. It cannot accommodate matter. So there is no matter in the pre-geometric phase. From pre-geometry to geometry, when the phase transition occurs, both matter and geometry co-evolve together, and the matter comes out of it. And that is how the fluctuations in the matter is related, and that is in a way, this is exactly what relates it to the cosmological constant, because 4 pi is just the surface area of a unit 2 sphere. So these two papers contain more details if you want to look up, and the cosmological constant paper is here, and these are acknowledgements to my co-workers. 2 of them will be speaking here in today's session. Thank you very much.
Okay, thank you very much. We have a tight schedule, but there is room for one question. If there is an urgent question, I can't see the audience, but if there is somebody who has a question, please feel, I see right in front of me and hand up. Yes.
Can you say? Well, I can't see you, but I can hear you.
Can you say something about flatness?
Flatness. The pre-geometric phase, if it is described by a conformal field theory in 2 dimensions and it makes a phase transition, the universe is very likely to be flat. But you can tinker with the dynamics of that phase transition to get non-flat spacetime. So those models look very awkward and built up, and the most natural model which emerges out of it is spatially flat. But this is not a rigorous proof. But since you asked, I just thought I should mention.
Okay, let's thank the speaker once more.